In the last lesson, we defined the set Z mod n, which we write as such, so Z and then subscript n. Now this is made up of congruence classes starting at 0 all the way up to n minus 1. The example that we looked at was Z mod 2. So Z mod 2 had the congruence classes of 0 and 1. And how do we think of this is if I take any integer, so a is going to be an element of z, I'm going to divide a by 2. So using the division algorithm, this would be a is equal to sum q times 2 plus r. So if we take each element divided by 2, we end up with some remainder. And the remainder are bounded by 0, so it's greater than or equal to 0, but strictly less than 2. And the congruence classes of this are just the remainder. So if I take every element and divide it by 2, it's either going to have a remainder of 0 or it's going to have a remainder of 1. If it has a remainder of 0, we're talking about our evens. So this is all our even integers. And if it has a remainder of 1, it's all of our odd integers. So we've basically taken Z and we've partitioned it into these two sets, a set of evens and a set of odds. But when we're thinking about Z mod 2, we're thinking of it again just in terms of its congruence classes, and there's two classes inside of there. So we've taken an infinite set and we brought it down into a finite set. So what we're going to be dealing with in today's lesson is we're going to now deal with modular arithmetic. So we've talked about the finite set Zn, which again is closely related to the infinite set Z. So it would be natural for us to ask the question, can we do arithmetic in relatively the same way as we would in Z in the integers, but this time in Z mod n? And the answer to that is, for the most part, yes, it's going to be almost exactly the same, but we just need to be a little bit careful. So this leads us into our first theorem for this video. So if I have two congruent classes A and B and they're equal to one another, so that's the sets of everything with remainder A, everything with remainder B. If I say that those two things are equal to one another, so those sets are equal, and again, the same idea for the congruence class of C and congruence class of D, this is all in Z mod n, then what is true is that if I treat this as equalities, I can add my right-hand side and I can add my left-hand side, and the statement is still going to be true in Z mod n. And it works exactly in the same way in terms of multiplication. So we look to add things, we look to multiply things in the integers, it's working in exactly the same way. All we're doing here is we're taking the representative of each of these congruent classes and we're adding those representatives together. So since this is an important thing for us, let's go ahead and let's actually prove this one here. All right, so back over to our whiteboard. So our proof is as follows. Now we have to do this for both addition and for multiplication. So we're going to do the easy one first. That's going to be the addition. So what we are given here is that the congruence class of A is equal to the congruence class of B. Now before I go any further than this, I can write this out using the theorem that we had in the last class, or the last video. So in the last video, we said when we have some A, congruence class A is equal to some congruence class C, this is true if and only if A is congruent to C mod n. So what I'm going to do is I'm going to transfer this congruence class of A is equal to the congruence class of B into this relationship here. So this means A is congruent to B mod n, because everything is in Z mod n. Now, by definition of congruence, this means that n divides the difference between A and B. So the distance between A and B, again, is a multiple of n, which, since this means this divides, that means that A minus B can be written as n times some x where x is going to be an integer. Now we're going to do exactly the same thing because in the theorem we had two equalities. So the congruence class of A is equal to the congruence class of B, and congruence class of C is equal to the congruence class of D, which again translate over into C congruent to D mod n, which translates over into n has to divide the distance between the two, so C minus D, which means if it divides, then C minus D is equal to n, and we'll do some y this time, where again y is an integer. All right, so the first thing that we want to do is we want to show that A plus B is equal to, sorry, not A plus B, it's A plus C is equal to B plus D. Again, this is all done mod n. All right, so the first thing that we are going to do is I am going to take these definitions here. So what we wrote A congruent to B, the congruence class of A is equal to the congruence class of B. We brought that down to A minus B is equal to n times x. And the congruence class of C is equal to the congruence class of D. We brought that down to C minus D is equal to n times y. We're just going to take these two equations and we're going to add them together. So I'm going to add together my left-hand side. I'm going to add together my right-hand side, because right now in this form here, we're talking about things in Z. So we can do the arithmetic exactly the same as we would normally do because we are in Z. So if I add these two things together, what am I going to get? On my left-hand side, I'm going to get an A minus B plus C minus D is equal to nx plus ny. Now I'm just going to rearrange my left-hand side. I'm going to group the positive things together, and I'm going to group the negative things together. So the positives are the A and C, the negatives are the B and D. So if I take A plus C, and I'm going to take that negative out since they're both negative, I'm going to have a B plus D is equal to, now on the right-hand side, notice those two terms both have an n in it. So I'm going to factor out that n. So this is n times x plus y. Now notice here, we have an A plus C, B plus D. Looks exactly like the form we have up here, A plus C, B plus D. So now what we're doing is we're going to try and work our way backwards here. So we have this little relationship. Now we want to put this back in terms of congruence classes. So what does this relationship tell us here? Well, notice that x plus y is an integer, because x is an integer, y is an integer. Add two integers together, it's still an integer. So this tells me the difference between A plus C and B plus D is equal to n times some integer, which means n divides what's on my left-hand side. So n divides A plus C minus B plus D. And in terms of our congruence relationship, well, that means that A plus C is congruent to B plus D mod n. Which again, based upon our last video with the if and only if statement, this means that the congruence class of A plus C is equal to the congruence class of B plus D. So that's our first part. So we proved that for addition. Now we want to prove this for multiplication as well. So again, all we're doing is we're showing that the basics of arithmetic that we would do in Z translates in relatively the same way that we would do it in Z mod n. Now I'm going to need this little bits of information up here, but I'll come back to that in a second. Whoops, there we go. All right, so this time around we want to show that AC, the congruence class of AC, is equal to the congruence class of BD. Now, unfortunately, I don't have a nice way to start this off exactly the same way we started off the other. But again, let's start off with this here. And what exactly does this mean? Well, if this is true, what needs to be true? That AC minus BD. Well, I should actually write this out in full. What this means is AC is, in fact, congruent to BD mod N, which again means N has to divide the difference between the two, so AC minus BD. So what we're going to do, we want to get to this point in time. I'm going to start here and show that I can work my way backwards such that this is in fact true. So let's start with AC minus BD. Now what I'm going to do to this is I'm going to add something to this. I'm going to add 0, but a very special 0. So let's say AC plus 0 minus BD. All right, so I don't want to just add 0 in there because that's not going to change anything. Let's actually put something in here that allows me to do a little bit of work. So instead of 0, I'm going to say 0 is equal to negative BC plus BC. So BC just cancels itself out. The negative, the positive gives me 0. So if I substitute this in, I have AC minus BC plus BC minus BD. And you'll see why I did this in just a second. Now let's factor this. Let's focus on the first two terms and the last two terms. So notice in the first two terms, what's common between the two? And that just so happens to be a C. So I'm going to factor out that C. So I'm going to have A minus B times C. And just think for a second, where have we seen this already? But we'll get back to that. And the last two terms, what's common between the two? Well, what's common is the B. So if I factor out B, this is going to leave me with C minus D. And again, we've seen this before, but where have we seen this? Well, let's scroll up for a second. In my original assumptions of what is true, I have A minus B is equal to N times X, and I have C minus D is equal to N times Y. So when I see A minus B, I'm just going to substitute in NX. When I see C minus D, I'm going to substitute in NY. So this is equal to NXC plus B times NY. So again, we have AC minus BD is equal to what's on my right-hand side here. But notice what's on my right-hand side. Both of those terms have an N. I can factor that N out. So AC minus BD is equal to N times XC plus BY. Now XC and BY, these are all integers. So if I multiply two integers and then I add the two integers, it's still an integer. So XC plus BY is an element of Z, which means that if that's an element of Z, I can take AC minus BD and it's just a multiple of N. So that means N divides the difference between the two, AC minus BD. And see, that's where we wanted to get to, because once I have here, well, I know if it means this divides, then this means that AC is congruent to BD mod N, which then back to the last video, this is true if and only if the congruence class of AC is equal to the congruence class of BD. So modular arithmetic, in terms of addition and multiplication, works exactly the same as it was in the integers, again, but we're dealing with congruence classes, so we still need to be a little bit careful. In the next example here, we're going to be going over how we would solve equations in terms of the Z mod N. So we'll see you next video.